Good morning, good afternoon, good evening, depending on where you're joining us from today, and welcome to Unpack the Stack, a webinar that's designed to provide an introduction to Quantinuum's next generation software stack, which we're releasing ahead of and to support Helios, the quantum computer that we will release later this year. Seyon, our principal manager of software engineering, will talk today through key components of the new stack, including Guppy, Nexus, and Selene. And so with that, I'll hand over to you, Seyon, and we can get going.
Thank you, Peter. Yeah, so welcome everyone. I'll be giving you an overview of all the new components of our software stack, ending at Helios at the bottom, which is our new hardware. I have a lot to get through. There's a lot of new pieces, so I'm just going to get started without too much ado. Okay, so firstly, an introduction to Quantinuum in case you're new to us or are not too familiar. We are, I believe, still the world's largest quantum computing only company. We have a large number of employees and growing quickly with a very deep scientific focus in our makeup. And as a company, we are really full stack, both in terms of expertise and solutions. So when I say full stack, that means all the way from applications right at the top, talking to clients, discussing their problems and coming up with algorithmic and scientific solutions in areas like chemistry, material science, artificial intelligence, cybersecurity, et cetera, but then going all the way through, implementing that in our software stack, compiling it, taking it through the web platform, providing an all-in-one platform for running these experiments, and all the way down to the world's leading quantum hardware based on our ion trap technology. So though that's not the focus of today's webinar, I will briefly mention what that hardware is. So this is our roadmap to universal fault-tolerant quantum computing in the near future. So far, we've seen record-breaking performance from our H1 and H2 systems, and later this year, we'll be launching Quantinuum Helios, which will be taking the qubit number up significantly and bringing gate errors down, which when Helios launches, you will see all the impacts of that. But for what's important for us is it also comes with a new platform for us to build a whole new software stack on top of. And that's what we'll be talking about today. Okay, so to tell you what the new software stack is, I first need to tell you what the old one was. So let's have a look at that. And this is a schematic in very simplified terms of how the old Quantinuum software stack looked. So everything below this line is things behind a cloud interface, things we host in our environment. And over here is the user's environment. Maybe they're running things on their laptop and want to run things on the quantum hardware or our emulators. So down here, there's the hardware, H1 or H2, for example, and some emulators of that hardware. And here, there's this component we'll talk about later on top of the hardware, which is the real-time engine, which is a piece of software which manages a program at execution time, a circuit as it's executing on the hardware. The portal to this for users is Quantinuum Nexus, which is our web platform. So that's sort of on this boundary, the gateway to our environment. The user might be programming in PyTicket. So some of you may have heard of Ticket, which is our Python compiler, the quantum compiler, and PyTicket is that Python package. So in here, someone might write a circuit, but they might be using third-party tools as well. So this includes NVIDIA Q2Q, Q-sharp, ORNL exec, and a host of third-party tools that can generate QIR. And PyTicket can generate QIR as well. QIR is an industry standard intermediate format for quantum programs. And this can then be taken in by Nexus, compiled and run on our systems. So that's how things look currently. And this is what we're moving to now with the new stack. Okay, so everything highlighted in green here is a brand new component as part of this new stack. So there's a lot to talk about. Let's start at the bottom. So here you can see that we have a new real-time engine. Now, this really is the fundamental baseline layer, which gives us a whole new swathe of capabilities that we can build on top of. And some simple changes at the bottom end up having some very consequential changes right at the top, which we'll see later. And to handle that, we have a whole new emulation framework called Selene. Because this real-time capabilities have changed, we need to change the emulator to be able to cope and do accurate emulation of the hardware. And then going into user land, you'll see that our new front end, the thing the user interacts with, is Guppy, which is a whole new programming language. Whereas PyTicket before was just a Python package that you stacked gates on top of, Guppy is its own full-featured programming language. And that compiles into our own intermediate format called Hugr. I'll briefly touch on why we have our own version of that here, but basically it boils down to by having control over components at every level of the stack, we can optimize performance throughout the stack. We can make sure that every layer of our stack is the best possible component to work with every other layer of our stack. All right, so we'll get to all of these, but let's start with Guppy. Put simply, Guppy is the most advanced programming language that runs on a real quantum computer. Now, what do I mean by that? In terms of quantum programming languages, there's been a lot of theoretical work, a lot of work into how quantum programming languages could work, what kind of semantics and abstraction should they have. And then, so that's at the very high level. And then at the sort of real level, working with hardware, things have been very, very basic up till now. They mostly boil down to, in terms of classical terms, trying to write assembly instructions by hand, or even lower level sometimes. It's individual gates, right, in a sequence. Because the theory of quantum computing is far ahead of the actual hardware, these things haven't really met. With Guppy, we're seeing a shift that bridges these worlds, right? This is a advanced modern programming language that can be compiled full stack and made to run on a real quantum computer when Helios launches. And it will continue to run on our systems going forwards, and will get more advanced as they get more advanced. Okay, so why Guppy in particular? What makes it special? There's three key things that I want to highlight. Those are that it's embedded in Python, it has a familiar syntax, and it provides safety. Let's dive into these a bit more. So by embedded in Python, what we mean is Guppy, though it is a full programming language, it actually is hosted inside Python. Now, Python is where most quantum developers already work. They may be using PyTicket, they may be using Qiskit, or a whole suite of quantum utilities and tools that the ecosystem has developed to work in Python. And also they tend to be scientists, so a lot of their other non-quantum scientific work, whether it be chemistry or just using NumPy or whatever, is workflows in Python. So what does this mean for the user? Concretely, it means Guppy fits right into your existing workflows. You don't need to move everything over into a whole new language, learn a whole new ecosystem, etc. Whatever you have in Python already works. You just add Guppy on top. Not only is it embedded inside Python, it looks a lot like Python. This is what we mean by familiar syntax. And for doing things like calling functions, doing arithmetic, doing control flow in particular, which we'll see later, having this really familiar Pythonic syntax means, concretely, for the user, it's really easy to learn. You don't have to study a book to learn Guppy. Most of the time, if you try and write Guppy as if you would write Python, it's just going to work. But if it doesn't, here comes the final part of Guppy. Unlike Python, Guppy is statically typed and compiled. What this means is that the Guppy compiler can do a lot of checking and safety checking for you before you ever run anything. And so even if you didn't quite get it right, the compiler will probably help you fix it. Why is this important? Unlike Python that you can run cheaply on your laptop or wherever you're running it, these quantum programs are designed to run on very scarce resources, i.e. quantum computers. You might have really long queue times. You might have expensive emulation, even if you're not running on a real device. Therefore, what you really don't want to do is run a program that is wrong, because then you'll only find out either during execution or when you get your results back, and you've wasted your queue time, you've wasted your allocation of the device. So the whole point with Guppy and other statically compiled languages like it is we want to prevent issues. We want to catch mistakes before you send them off. And so concretely, what does safety mean to the user? It prevents expensive mistakes. Okay. These fundamental aspects, when they stack on top of each other, they change how you think about quantum programming. When you move from picturing circuits as these like 2D wire diagrams into thinking about writing software in a language like Guppy, you naturally start doing modular software engineering. And this kind of modular approach is really important as we scale into the future. Quantum programs and quantum computers are not going to be things you can manage by handling every single thing by hand. We need to be able to produce well-tested, trustable components and then reuse them in a modular way. And that's how we do engineering. Beyond that, the natural control flow and classical logic that Guppy provides alongside your quantum logic is absolutely essential for programming quantum error correction. And thanks to our flexible ion trap technology with fully connected architecture, where the ions can be moved around to interact with any other ion, we can, on top of that, offer very, very flexible quantum error correction built entirely in software. And Guppy is the software that this error correction will be built in. We can try arbitrary codes because we're not limited by connectivity, and Guppy lets you do that very easily and naturally with natural programming. But it's not just error correction. We found that having these extra capabilities, though they are simple to explain, unlocks a whole new ways of designing novel algorithms that you just simply wouldn't have thought of if you weren't thinking in terms of natural programming. Okay, so I don't have time to go into every single Guppy feature because there are a lot. It is a full-featured modern programming language. So I'll flash some of them up here. And if you're interested, feel free to ask questions about it at the end and we can cover some of these. But some things I want to highlight quickly are it has like very powerful compile time metaprogramming in Python. You can do full classical computation in real time with the quantum computation. This includes integer arithmetic, floating point arithmetic, and so on. You get full control flow, as I mentioned. You can work with data structures, which really helps structure your code. You can with arrays, tuples, user-defined types. Arrays are really important because it lets you have scalable quantum programs. Now you can write programs that even if your qubit number is going up, your program size doesn't, so your compile time doesn't. This is very important going into the future. It has first-class functions, so you can do higher order programming with Guppy. And finally, it has full legacy support. So we're not expecting everyone to just rewrite all the circuits they had previously. If you have a PyTicket circuit, and lots of things can be converted into PyTicket, you can simply load that as a Guppy function into your program, and then call it just like you would call any other Guppy function, which helps make the transition really, really smooth. Okay, and then finally, just a quick note on Hugr. So Hugr stands for the Hierarchical Unified Graph Representation. You can think of it really as a generalized circuit, generalized not just to include quantum gates, but also classical operations. So it can include a full classical program and full control flow and structure. So this schematic here, if you zoom in on the inside, it looks like a circuit, but there's more structure going on. So here we have a condition, an if-else condition, and then the whole thing is actually a repeatable loop. So these kind of control flow constructs and things like function calls are built into the Hugr, and it can capture that whole thing. Why is this important? Because as we move into the fault-tolerant era, it's going to be really, really important that we can optimize quantum programs, taking into account both the quantum and classical parts when we reason about our optimization. So obviously, we have expertise coming from Ticket, and Ticket in the new versions will be moving to operate on Hugr. So Hugr is the data structure that Ticket is going to be operating on as it optimizes these quantum classical programs. Again, if you have more questions about Hugr, we can tackle that in the Q&A. All right, so I've said a lot about Guppy so far in terms of words, but the proof is in the pudding. So we should take a look at some Guppy code. To do that, let's go back to that quantum error correction application that I mentioned before. So we're going to do some really, really basic quantum error correction. Specifically, we're going to do fault-tolerant state preparation. Now, if you're not familiar with quantum error correction at all, there is a lot that I could cover. It's a very deep field. But for our purposes for today, let's keep it simple. It boils down to two things for us. So if you need to protect 1 qubit of information from errors happening, because errors will happen on the device, and quantum error correction is all about protecting your program from those errors. If you have 1 qubit of information, we're going to use multiple physical qubits to encode that information in for redundancy. So if an error attacks any one particular physical qubit, it's easier for us to recover from that error because we have some redundancy. On top of that, we have specific encoding protocols, or codes, as you'd call them, that lets us detect and correct a certain number of errors. And if you do that very diligently, then you get fault tolerance, effectively. You get a program that can correct itself as it runs from errors. Specifically, this is going to get a bit detailed, so if you are familiar with the codes and QEC, we're going to be looking at a 713 Steam code state preparation. These numbers effectively mean in the Steam code, we're going to use 7 physical qubits to encode 1 qubit's worth of information, and it protects us from errors at a distance of 3. And all we're going to do is attempt to encode 0 in the Steam code into these 7 physical qubits. And the protocol works very simply. We run a circuit that attempts to encode 0, and if there are no errors, it would. But if an error occurred while we were encoding 0, we have a check that would tell us an error has happened. And if we detect an error, we simply try again. Now, here's where the Guppy magic is, really. So those of you familiar with programming quantum circuits in legacy tools, if you think about how you would write this logic of if error detected, try again, you might be able to come up with a convoluted way, but you can probably imagine it would be quite cumbersome with a flat circuit. You'd have to unroll everything into a certain number of attempts. You'd do something like do the state preparation, do the check. If it failed, do the state preparation again. And then you get this really long circuit, and it doesn't really look like what we've written here, which is very simple logic. What Guppy gives you is the ability to go from this simple logic in your head to simple logic in code. All right, let's go to code. Okay, so hopefully you can see my code here. I'm in a Jupyter notebook. We're going to start by just importing some stuff. And now here is the circuit that we're actually going to implement. This is the encoding circuit we're going to use. Here are our 7 physical qubits. And then there's one more that we use to do our check. That's our ancilla. So this first part here is doing this preparation onto those qubits. And then these 3 C-naughts here do the check onto the ancilla. And then we measure the ancilla. If that ancilla measurement is 1, we know we've detected an error. If it's 0, we haven't. And we're going to implement this in Guppy as a series of functions that build on top of each other. Okay, so here is some Guppy. I mean, as I say, we're in a Jupyter environment, so far we've only looked at Python, right? We're in a Python environment. And this is all here still Python. I'm just setting some parameters I'm going to use. A random seed so we can replicate things, the number of shots we're going to use, number of repeats, and the number of qubits we need. It's 7 for the encoding plus that extra 1 for the ancilla. And here we start seeing Guppy. So whenever you see this @Guppy decorator, what that means is the thing that is decorated with that is not actually Python, it's Guppy. So this function, for example, though if we're just glancing, it just looks like any other Python function, and that's by design, it is actually a Guppy function. And therefore, when this runs, in Python, it won't actually run this function. What this Guppy decorator is doing is taking that whole function and compiling it into Hugr so that we can then submit it for remote execution or local or whatever. Okay, so let's look at our first function here. This is doing that first part of the circuit where we're going to get our 7 qubits and do our state preparation. So we start by getting an array of 7 qubits. Array is a Guppy type, and here is qubit. We then do the Hadamards that we wanted to do, and then iterate over our C0 indices to do the C0s we wanted to do. Now here you'll see this function returns this Steen qubit type. And that up here we'll see is a Guppy struct, and this is custom user types in Guppy. What this means is instead of typing array qubit 7 all the time, we can put it inside our new type and treat this as a fresh new type, which makes for much more readable and scalable code. And note here also, arrays here are much more typed than you would expect from Python. So this is an array of qubits, and we have a type level size here saying this array is always 7 big. This is really important for being able to manage resources so that the compiler can reason about how many qubits you've used and make sure you're using the right number of qubits when putting functions together. Okay, so that's our non-fault tolerant preparation, our initial thing. Now we need to do the check. So we can write another function here called flagged fault tolerant 0 that can start by calling the one we've already defined. So here you can see Guppy functions can call each other, and this is how we naturally build up structure rather than writing one big, unable to read program. And then we prepare an ancilla, do the C0s we need for the check, and then return the prepared qubit and a measurement of that ancilla. So that's what this return type is telling us. We're going to return the prepared qubits and the measurement saying whether there's been an error. Okay, now we have all the pieces to express the logic we talked about here, this top level logic. And we can do that in a Guppy function too. So that's our final function here, which we're going to call count attempts. And it's as easy to write as the text was on my slide, effectively. We loop over some number of attempts. We attempt to prepare a 0. And if it has not failed, i.e. no error was detected, we output how many attempts we took to succeed and then stop trying. So this is fairly complicated control flow, but expressed in very simple Pythonic syntax that's very readable. Here you see an extra little power feature of Guppy. This pi statement lets you pull in values from the outer Python scope. So the maximum number of attempts we're going to take, I've actually put in the Python here because it's just a constant value. And using this pi statement, I can pull that into Guppy from the outer Python scope, and that will be available at quantum runtime. Note also this result function. With Guppy, unlike with traditional tools, it's not just the measurement results of your quantum circuit that get reported back to you. You can, in fact, at any point in your program, report any value, as long as it's one of these simple types. So in this case, it's just an integer, and we can just send our integer out saying, I'm going to stop, and it took this many attempts, which can make for much more compact and convenient result formats coming back, rather than just having to send out streams and streams of zeros and ones. Okay, and then this final line is where we can do Guppy type checking. So as I said, these can't be called like a normal Python function. It's a Guppy function, but before trying to run it, we can type check it. And that will check our entire program that we've written so far. So let's do that. And Guppy is not happy. And this is what I meant about the compiler really helping you avoid mistakes. So here we get a very readable error from Guppy. And that's not as easy as it sounds to do. It's a very underappreciated feature, getting good errors. And Guppy really goes out of its way to give you good, helpful errors. It points to where something went wrong, and it tells you exactly what went wrong. What it's telling us is every time we do our attempt, we allocate 7 qubits, but we only have 8 total available. So if we try again, and without discarding the ones we don't need anymore, we're going to get a qubit leak, which could lead to, and a qubit leak is a very wasteful thing to do. It would generally mean an incorrect program. So Guppy prevents this using linearity. And here specifically, it tells you with a hint, make sure that you discard or consume the qubits to avoid the leak. And we can do that very simply by discarding that array before trying again. Okay, try again, and Guppy's happy. All right, so before we carry on with the notebook, let's find out a bit more about the stack. So the next component I want to talk about is Quantinuum Nexus. Nexus is, it's not brand new, it's been around for a while, but it's been upgraded to support all of this new tooling. And a brief overview of what Nexus is, it's our all-in-one cloud software as a service platform. And this means it's our one portal for users and clients and customers to get hardware access. It's what hosts our premium emulation services that run on the cloud. And it provides a whole suite of experiment management tooling. So you can manage your jobs, you can collaborate with other researchers or team members, sharing your work, sharing your results. And it provides a lot of tools for administrators as well to set quotas and caps and manage what members of the teams have what access to what hardware. Okay, we can then go away and submit our program to Nexus. Before we do that, just a quick word, there's this, I'm going to define this quick utility function. All we're going to use it for is once we get our results back, we're going to use it to average the number of attempts we took to prepare our state over the shots. Okay, so the Python interfaces to Nexus is called QNexus, this package QNexus. I've already imported that. So I can start by creating a new project in Nexus called Selene Nexus. And once I have that project, I can upload and configure my job. So it's pretty simple. Rather than doing check like we did before, this time we're going to do compile on our program. Now this gives us back our Hugr that I talked about before. And Hugr is what gets sent over to Nexus. And we're simply going to call the upload function and get a program reference. Once we have a program reference, we need to configure the backend that we want to run this on. And so we're going to configure an emulator. And specifically, we're going to configure the emulator to model the device. Now, this model won't be final until the actual launch of hardware. So this is actually just a demo model. So don't take any of the results too seriously. Take it with a huge grain of salt. But it shows us exactly how things are going to work and with a demo model. And if you were submitting to a device rather than an emulator, it would look very, very similar to this. Once we have those two components, we can just tell Nexus to go run that job over our number of shots. Okay, so let's do that. Nexus has accepted our job, so we can switch screens. This is our Nexus web portal, nexus.quantinuum.com, and you can see that my job has turned up here. It's come up as submitted. And while that runs, we can go away and learn a bit more about some other components. Okay, so a lot of what's possible in Guppy is due to our new real-time engine. To explain that, first let's look at how things used to work in the old real-time engine. As I said, users write circuits. These are, you can think of these effectively when they get sent to the device as a big list of gates with some measurements at the end. Typically, that's how that works. Do this on some qubits, do this on some qubits, do this on some qubits, measure them all, send the results back. So typically, that list of gates would get sent to the device. The real-time engine would just, in one straight shot, run through all of them, and then maybe repeat that if you asked for repeats. And once it's done doing that, it will send all of the results back to the user. And that's all the flexibility the user gets. So it's a very simple, straight line program system. But the new real-time engine is a lot more capable. It's a lot more dynamic. How this works is now the program can send some gates over to the system, which will execute, and then it can request measurements. When the program requests measurements, all of those gates preceding will run, and the real-time engine will manage sending measurements back to the program. At this point, the program can branch based on that measurement, say if-else branching, do this or that, or loop, repeat. If this thing hasn't happened yet, try again, which is what we're doing. And it can also do full classical computation with those measurement results. This is essential for quantum error correction, do integer arithmetic, array lookups, etc., etc. And once it's decided what the next thing it wants to do is, it sends more gates out, and so on and so forth. So it's a much more dynamic environment where the program and the ion trap are in constant communication, running these adaptive, efficient programs. And because the real-time environment has become so much more powerful, that's why we needed to build out our own emulation framework. So we needed to build this from scratch to be able to replicate all the capabilities of Helios and the hardware going forward. And that's Quantinuum Selene, our emulation framework. I say framework because it's actually very flexible. It's designed to be able to be deployed in a variety of scenarios and for a variety of use cases, and it does that by having a very flexible plugin system. There's three key kinds of plugin for Selene. One is the simulator it uses. So the distinction I'm making between emulator and simulator is a simulator just in your classical computer calculates the evolution of your qubits state in some way. Whereas the emulator, it's actually tracking the full behavior of the QPU. This includes all the classical computation. This includes things like ion transport, etc. So the simulator is just one part of that. So we can use out different simulators, including third-party tools, via the plugin system to simulate using whatever is the best method of simulation for that program. So the most general is state vector, for example, but that can get very expensive. For certain types of circuits, Clifford circuit, you can use stabilizer simulation. So Selene offers that via using STIM, and so on. The second component is the error model. So to emulate the device, we need to be able to model the errors that occur on it. And Selene offers a flexible error model interface. So you can use some simple ones that you can tweak, or you can use very detailed ones about the device and swap them in and out. And finally, the runtime component is needed to model things that are happening in real time, like I talked about, such as real-time calculations of ion transport, dynamic qubit allocation, things like this. And then with this flexibility, that gives us the ability to have two kinds of Selene instance. So most of Selene, the core, the actual central core elements, are fully open source, just like Guppy, Hugr, and Ticket. And it's distributed as Python packages. This enables fully local development. You don't need to have Nexus access to use Selene. Open source core Selene is available straight out of the box with Guppy Lang. It's built in. It comes with the state vector and stabilizer simulation that I mentioned. The state vector simulation is powered by the Quest simulator and stabilizer by STIM. And it comes with all of the extensibility I already mentioned, so you can use your own plugins, third-party plugins, whatever you like. But then our own proprietary plugins give us the cloud-hosted, superpowered Selene. Now, this is the emulation provided via Nexus. It allows us to provide premium backends like GPU-based matrix product state simulators that are powered by NVIDIA Quantum, and more to come. And it allows us to provide really, really accurate, high-fidelity emulation of our devices that only we can provide. Okay. With that, then, we can go back to our demo. And while we wait for things to run on Nexus with high accuracy, we can play around locally. So, as I said, Selene actually comes built into Guppy Lang via this .emulator interface. So this is our count attempts function again, but rather than calling check or compile this time, we're going to call emulator. What this does is compiles the program into an emulator object that we can run. So we just request the number of qubits we need for that, and that gives us an emulator. And then we can configure it. So we're going to configure it to use stabilizer simulation because our circuit is a fully Clifford circuit. We don't need full state vector simulation. This will go much faster, which is great. We can set our seed, set the number of repeats we want to do. And in this case, I'm going to use a progress bar so we get a nice progress bar when it runs. And once we have our emulator, we simply call .run on it, and that returns our results. And then we're going to send our results into our mean attempts function to get that averaging that I talked about earlier. So let's run that. Should run pretty quickly. And this is a perfect noiseless simulation. Therefore, there are no errors in our circuit. Therefore, we would expect the state preparation to succeed on the first attempt every time. And that's exactly what we see. Even though we ran 1,000 repeats, our mean attempts is 1, because every single time it succeeded the first time. Obviously, that's a bit boring, so let's try and add some errors. We can use this built-in depolarizing error model that comes with Selene as a plugin, and we'll set some probability of gate errors. So this is a single qubit gate error of 10 to the minus 3 and a 2 qubit gate error of 10 to the minus 3. We can now just update our emulator to include this error model here and rerun it. And if we do that, we now see our mean attempts has gone up a tad. And this makes sense. There is now some probability of error in the gates. Therefore, some of the time, in some of the shots, we detected that error and retried until we succeeded. Okay, so now that we have some intuition, we can try playing with the parameters to see if things make sense. Let's try putting our 2 qubit error up. Now, what do we expect to happen here? Our 2 qubit error rate, the probability of a 2 qubit error has gone up. Therefore, it's more likely that a state preparation will fail. So our average number of attempts should go up. So if we rerun that, it's exactly what we see. Our average number of attempts has gone up. Okay, now that we've played around locally, we can see what our Nexus results are doing. So let's go back to Nexus. And good news, our job has completed. So we can use QNexus to pull down the results we need. We can also view them on the web interface, but for our purposes, it's useful to be able to just process it here. So we're going to download our result and send them through the exact same mean attempts function that we used locally. And if we do that, it takes a little bit of time for it to talk to Nexus and get the results down. We see things have all gone well, but we're getting a mean attempts number that's lower than we saw with the 10 to the minus 3 depolarizing error model. Now, as I said, take the model we're using for the device with a very, very big grain of salt. But at face value, what this means is for this experiment, the effective error rate happening remotely on our device model is better than we were getting with this 10 to the minus 3 depolarizing error, because it took fewer attempts to succeed on average. Okay. And with that, I don't have much more to say other than to say, if you want to learn more, we have quite an extensive number of docs. We have a full language guide for Guppy, a number of worked examples that are all these downloadable notebooks that you can run and learn from. And they're all available at guppylang.org, including how to use the emulator, etc., etc. So scan this QR code, go to the link to learn a lot more.